Hello, this is the first part on chapter 6 that deals with propositional logic. What are the building blocks of Boolean formulas? The building blocks consist of three parts: constants, variables, and connectives or logical connectives. Constants are simply 0 or 1. We also call them bits. We interpret 1 as true and 0 as false. Why do we use two different terms for bits? Why do we call it constants sometimes and bits sometimes? They refer to the same thing. The term bit is used when we talk about Boolean functions and circuits, and the term constants is used when we refer to Boolean formulas, which is the topic of today's lecture. A variable is just an element in the set of variables. As usual, we will denote them by x, y, z, and so on. We denote the set of variables by capital U, and we emphasize that the set of variables does not contain the constants, does not contain 0 and 1. So when we refer to a variable, it is not a constant. And when we refer to a constant, it is not a variable. Connectives are used to build longer formulas from shorter ones. We denote the set of connectives by calligraphic C. We have different types of logical connectives. We have only one connective, which is unary. This connective is called negation. Negation of a variable is denoted by not a, this strange symbol before the a, or bar a, over bar a. There are several types of binary connectives, and which we also denote by this upside down V or a dot, or also denoted by a V or a plus. A binary connective is applied to two sub-formulas or to two formulas. We later show the relation between the binary connectives and the Boolean functions that are attached to these binary connectives. But at this point of time, think of the binary connectives simply as glue that takes two formulas and glues them together to form a new formula. A connective has arity J if it is applied to J formulas. So the arity of the negation is 1, therefore it's called a unary connective. The arity of and, or, is 2, therefore it's called a binary connective. So unary refers to 1, binary refers to 2. All of these refer to the arity of the connective, which specifies the number of formulas it's applied to. In this course, we will focus on arity of 1 and 2. Negation has arity 1 and has arity 2. We form Boolean formula using parse trees. Here's an example of a parse tree. What is a parse tree? It is a rooted tree, so you see we have here leaves, and we have directed edges towards the root. And we label the vertices of the parse tree. The vertices of the leaves are labeled by variables x, y, or by a constant, 0. The interior nodes, these are the nodes, the vertices that are not leaves, are labeled by connectives, or, and, not. Notice that when the in-degree of a node is 2, the connective here is or, its arity is 2. The in-degree of this vertex is 1. Therefore, we write here a connective with arity 1. We only have one connective with arity 1. This is negation. And the root has arity 2. We label it with and, which also has arity 2. Now this parse tree corresponds to the Boolean formula x or 0. This is x or 0 and not y. Here's not y. Okay? So we will talk about what parse trees are and how they define Boolean formulas. We will also talk about subtrees hanging from a node. So if we look at this OR, at this vertex labeled OR, the subtree hanging from it contains 3 vertices and 2 edges. And of course, it will define a subformula, the subformula x or 0. Formally, a parse tree is a pair G comma pi, where G is a rooted tree consisting of vertices and edges, directed edges. Pi is a function that assigns labels to the vertices of the parse tree. These labels could be constants, 0 or 1, variables in the set U, or logical connectives. Now, this labeling pi has to satisfy 2 conditions. The first condition is that leaves are labeled by constants or variables. Therefore, if V is a leaf, then pi of V has to be either a constant or a variable. An interior vertex, this is a vertex that is not a leaf, has to be labeled by a connective. Now, the connective that is labeled must have an arity that equals the integrity of V. So if V is an interior vertex and the label of V is pi of V with some arity, the arity must equal the integrity of the vertex. In this course, we will usually use only unary and binary connectives. So unless we state otherwise, the parse tree has an integrity of at most 2. Okay, now we want to define Boolean formulas. Let me tell you the plan of how we're going to do this. So, Boolean formulas are simply strings that contain constants, variables, and connectives, and parentheses. Okay? So, we will use constants, variables, connectives, and parentheses in order to construct Boolean formulas. How will we define Boolean formulas? We will use parse trees to define Boolean formulas. Now, the definition that goes from a parse tree to a Boolean formula is constructive. It will use a method called in-order traversal of a parse tree. For those of you who do not know what in-order traversal of a parse tree is, I will define it shortly. Okay, before we go through this definition that begins with parse trees and then defines Boolean formulas, let's get some intuition of what a good formula is and what a bad formula is. So a formula could be open parentheses, A and B, close parentheses. Same thing with an OR. But the third line is not a Boolean formula. Okay? You see immediately that there are some problems here, right? There is no open parentheses, and you have 2 connectives following one each other. But we want to formalize why this is not a Boolean formula. This is a Boolean formula. A and B, or A and C, or 1. Now, in general, if phi and psi are Boolean formulas, then open parentheses, phi or psi, close parentheses, is a Boolean formula. And in general, if phi is a Boolean formula, then open parentheses, not phi, close parentheses, is also a Boolean formula. So if we have 2 Boolean formulas, we know how to form a new one from it. If we have only 1 Boolean formula, we also know how to form a new formula from it. Okay, now we will stick to parse trees and show how they are parsed to generate Boolean formulas. So this slide describes how in-order traversal of a parse tree takes place. And the in-order traversal generates a Boolean formula that corresponds to the parse tree. Okay? The algorithm, or the in-order traversal, is a recursive algorithm. So we need to describe the base cases and the reduction rules. The base case is when the number of vertices in the parse tree is 1. In this case, the parse tree consists of a single vertex, which is also a leaf. The leaf is labeled by a constant or by a variable, and the formula that this parse tree represents is simply the label of the root. So in this case, we have a single node, and something is written here, let's say the constant 0, and therefore it represents the formula 0. It could be a single root with a 1 in the label, and then it would represent the formula 1. And it could be a single root labeled by x, and then it would represent the formula x. This is the base case. Now we go to the reduction rule. The reduction rule applies when the number of vertices in the parse tree is greater than 1. Now we look at the root of the parse tree, and we consider two cases. Either its integree is 1 or its integree is 2. These are the two cases we need to address because we assume that the integree of every node in the parse tree is at most 2. If the integree of the root is 1, then our tree looks like this. The root must be labeled by the not connective, because not is the only connective whose arity is 1, and there is a subtree G1 which hangs from this root. Now, let G1 denote the rooted tree hanging from the root, and now what we do is we restrict the labeling pi to the vertices inside G1. This is called V1. And we apply the in-order traversal recursively on G1. This in-order traversal generates a formula denoted by alpha. Here's alpha. Now, what is the formula which corresponds to the whole parse tree? It is not of alpha. So we return not of alpha, in parentheses, of course. Good. What do you do if the integree of the root is 2? Well, in this case, the root is labeled by some binary connective, which I just wrote here a star. This could be an or an and, or any connective. And you have two subtrees hanging from the root, G1 and G2. Each of these subtrees represents a Boolean formula, which we get by applying an in-order traversal over the corresponding subtree. So we get the formula alpha for G1 and the formula beta for G2. Now, what is the formula that corresponds to the whole parse tree? It is alpha star beta, where star is the label of the root. This is in-order traversal of a parse tree, and this is how we define Boolean formulas. Okay? So once we have a parse tree and we have a subtree that hangs from a node V in the subtree, we apply in order to the whole parse tree in order to get a Boolean formula phi, and we can apply in order starting from the subtree hanging from V to obtain a subformula of phi. So in this depiction, we have a parse tree. If we apply the in-order traversal to the whole tree, we get the formula phi. If we apply the in-order traversal to the rooted tree hanging from V, this is marked in yellow here, then we get the formula phi prime, which is a subformula of phi. Now, consider all the parse trees over the set of variables U and the set of connectives C. Each such parse tree defines a Boolean formula. The set of all Boolean formulas defined by these parse trees is denoted by BF of U, C. These are Boolean formulas over the set of variables U and the set of connectives C. Often, to simplify notation, we abbreviate and simply write BF whenever the set of variables and the set of connectives is clear from the context. Now, we will use equivalent notation for for our connectives. So we can write or, v, or plus. This is the same thing. We do not make any distinction between the plus, the v, and the or. We regard them as equal symbols. Therefore, the Boolean formula open parentheses a plus b close parentheses is the same formula as the formula open parentheses a v b close parentheses, which is the same formula as open parentheses a or b close parentheses. I want to emphasize that by equality here, I'm referring to string equality. The first string equals the second, the first symbol in the string equals the first symbol here, the second symbol equals the second symbol over here, the third symbol is the same, and so on. So we compare the strings symbol by symbol, and we regard them as equal, even though there's a plus here, a v here, and an or here, because as I said, I regard a plus, an or, and a v as the same thing. And the same equality holds with respect to this dot, the upside down v, and the and. The same equality holds with respect to this strange symbol, the not, and the overline. The same equality holds with respect to XOR and our plus surrounded by a circle. And therefore, if I look at a more complicated formula, it equals what is written here on the right, because all I did was I replaced the v by a plus, which I said was the same thing, the upside down v by a dot, and this funny line with an overbar. Okay, I want to emphasize that very often we omit parentheses when we write formulas. And the reason is that we can apply precedence rules as we do in arithmetic. Therefore, a formula of the form a dot b plus c dot d, which actually means a and b or c and d, should be given these parentheses, and we know how to add these parentheses by applying the precedence rules in arithmetic. So you do first the multiplication, then you do the second multiplication, and only then you do the so-called addition. Only here, this is not multiplication, this is and this is not addition, this is or. Okay, so please do not be confused. When we talk about Boolean formulas, the plus denotes an or, the times denotes an and, the circle with the plus denotes a XOR. I want to introduce a few new connectives. The first connective I want to introduce is called the implication connective and is denoted by an arrow. And the multiplication table of the implication connective is depicted over here. So you see that 0 implies 0 gets the logical value 1, 0 implies 1 gets the logical value 1, 1 implies 0 gets the logical value 0, and 1 implies 1 gets the logical value 1. Now, a way to remember what the implication connective is all about is that A implies B is true if and only if A is less than or equal to B. And here I'm referring to A and B as variables that get values from which are either 0 or 1. So I say, if I have a bit here and a bit here for A and B, this bit implies the second bit if the bit corresponding to A is less than or equal to the bit corresponding to B. Okay, so you can think of implication simply as a less than or equal sign. Now, the implication connective is not commutative, as you can see immediately that 1 implies 0 is 0, while 0 implies 1 is 1. Okay? This connective is called implication since it models the natural language template y if x or if x then y. Okay? We note that x implies y is always true if x is 0, right? Look at this row. If x is 0, then all entries in this row are 1. Okay, so false implies everything. Okay, this is our rule for implication. Two more connectives that I want to describe are NAND and NOR. Now, NAND is simply a shorthand for the not of the AND of A and B, and NOR is shorthand for the not of the OR of A and B. Okay? What are the multiplication tables of NAND and NOR? Here we see them below. We just took the multiplication table of AND and inverted all the entries. And the NOR, we took the multiplication table of the OR and inverted all the tables, all the entries. Now you may ask yourself, are these two new connectives, NAND and NOR, are they commutative? Are they associative? And I strongly urge you to check it. The next connective that I want to describe is the equivalence connective. It's denoted by a left-right arrow, an arrow in both directions. And this is in fact an abbreviation for P implies Q and Q implies P. You see, here is the multiplication table of the equivalence connective. And you can see that the value of this connective is true only when the two arguments are equal. This is along the main diagonal. So x is equivalent to y if and only if x equals y, otherwise it's false. Now, when we talk about parse trees or about Boolean formulas, order matters. You see, here in the root we have the label of the implication connective, which we saw is not commutative. So what we conclude is that it is important that we understand that this part is the left subtree hanging from the root, and this part is the right subtree hanging from the root. Because if we were to transpose them, we would get a different formula, which would not be equivalent, because implication is not commutative, right? So you cannot expect x or 0 implies not y to be equivalent. It's not equivalent to not of y implies x or 0. Okay, so order matters, and this is important. Let me summarize what we have seen. We have defined variables. These are just formal symbols, x, y, z, and so on. We have defined logical connectives, not, and, or, nor, NAND, implication, and equivalence. We attached Boolean operators to these logical connectives, but at this point of time it's not clear what exactly this means. We will see that later. We defined parse trees, which are nothing but rooted trees labeled by variables and connectives. And we use parse trees to define Boolean formulas, and these Boolean formulas are defined by an in-order traversal of the parse tree. Thank you.